In the first part we talked about conditional probabilities, but most of the time we were using like a two-way table, or what we call a contingency table. Okay? Well, what if you're just given probabilities and not actually given a table to pull numbers from? Okay? In this case, we're going to be using this formula here. So the probability of event A, given that event B occurred, is the probability that A and B both occur, divided by the probability of B. This is actually very similar to the conditional probability we were using when we were in the table. Because remember, the numerator was that they both occurred, and the denominator was just how many were in part B. So let's go back to my table for a second. Okay, I think I went this. Oops, I went too far. Sorry. I think it's not keeping up with me. Where's my table? Okay. So like when we were finding the probability that it was they were on the bus given they were female, right? The numerator was this 32, that they were both on the bus and that they were female. If you remember, that was what I had in my formula on the top. Okay, and the denominator looked at just the females, and that's what I had in the denominator. Okay, so what I have now is the exact same thing I was doing, except now it's written in terms of probabilities instead of written in terms of counts. Okay, I never really gave you a formula for the counts because we just looked at how many fit in B, and then the numerator is how many had both of these true. Okay, but now it is written in terms of probabilities, so it's really the same thing we were doing with contingency tables. Okay, so you're going to use this when you're given the probabilities or percents, and you do not use this when you're doing a contingency table, even though I just made the connection between the two. In the contingency table, you're not really using the probabilities, you're going to be using the counts. Okay, we can take this formula and we can actually rearrange it and stuff, so there's like 4 different ways you can write it. I could also say it's the probability of B given A is equal to the probability of A and B divided by now the probability of A. Right, your denominator is always going to be what's the given part. Okay, you notice the numerator is the same in both of these statements, and I showed you that when we had the bus given the females and the females given the bus. Okay, and now we can also write it as the probability of A and B, right? And all I'm going to do is multiply both sides by this, just a little algebra, and we get the probability of A given B times the probability of B, or the probability of B given A times the probability of A. And that would both be an expression for the probability of A and B. Okay. One thing to remember is the probability of A given B is not the same as the probability of B given A. And again, if you go back and look at where I talked about the probability that you're on the bus given you're a female, and the probability that you're female given you're on the bus, those two numbers were not the same. Okay, so it's important the order of the A and the B when on these conditional probabilities. Hopefully you realize the probability of A and B is the exact same thing as the probability of B and A. In that case, I can switch the A and the B around. Okay, so let's look at a problem where I'm given the probabilities. So by 2020, it's predicted that 2% of Americans will be senior citizens living in poverty. It's predicted that 17% of all Americans will be senior citizens in 2020. So what percent of all senior citizens will be living in poverty? Okay, so the first thing we're actually going to want to do is just write in symbols what it is that we know. Okay, but sometimes it's even useful to use this one letter. For a lot of what I've been doing, I've been writing, like I wrote the whole word bus out, I wrote the whole word female out. Okay, now I'm just going to use one letter to represent something. So the two things I'm talking about here are senior citizens and living in poverty. Okay, so all we're going to do is just make my two events, one be S, so whenever you see an S, that means it's a senior citizen. If you see a P, that means that it's a person living in poverty. Okay, next we're going to write in symbols, we're going to write the probabilities that we know. Okay, well there's two probabilities here. One is the 2% and the other is the 17%. Okay, so let's look at the 17% first, because that's probably the easier of the two. So it's predicted that 17% of all Americans will be senior citizens. This is a good time to pause the video and see if you can figure out how to write these two percentages before I talk about them. Okay, so 17% of all Americans will be senior citizens. I'm not talking about anything about poverty. I don't have any conditional probability here. It's just if I pick American, because that would be my population, 17% of them are going to be senior citizens. So that's just straight, the probability that you're a senior citizen is 17%. Okay, so that'll be in 2020. Okay, and then the other one I have is that 2%. So it's predicted that 2% of Americans will be senior citizens living in poverty. Okay, so am I given that it's a senior citizen, or am I given that it's in poverty, or I'm not given anything, in which case it would just be senior citizens and poverty. So pause the video again, think about this. What I'm telling you here for the 2%, it's 2% of Americans will be senior citizens living in poverty. That means they're going to be both senior citizens and living in poverty. So in that case, it's going to be the probability of S and P is that 2%. The probability of S is the 17%. Okay, next I'm going to write, using symbols, I'm going to write the probability of what I'm trying to find. So maybe we need to reread the whole thing again. Okay, so by 2020, it is predicted that 2% of Americans will be senior citizens living in poverty. It is predicted that 17% of all Americans will be senior citizens in 2020. Okay. What percent of all senior citizens will be living in poverty? Okay, so again, think about what it is that I'm trying to find here. Is one of these a given? Okay, chances are it's not probability of S and P because I gave you that number. Okay, so kind of your choices are, is it the probability of S given P or the probability of P given S? Okay, so again, pause it and think about what probability I'm trying to find. Hopefully came up, it's the probability that you're in poverty given that you're a senior citizen. So what percent of all senior citizens, that's the get, you know it's a senior citizen, will be living in poverty. Okay, and now I'm trying to find the probability of P given S. Okay, refer back to the other slide. So that's the probability that both of them occur divided by the probability that you're in the last, what you're given, which in this case is senior citizen. Okay. Now, am I given both of these two numbers? Probability of P and S? Well, up here I wrote the probability of S and P, and that would be the same thing. So the numerator is going to be the 2%. Okay, and the denominator is going to be the 17%, okay, which gives me 12%. So now you should be actually write a sentence that tells you what the 12% represents. Again, pause the video, think about what the sentence is going to be that you're going to write. Okay, so in 2020, about 12% of all senior citizens will be living in poverty. Right, so given you're a senior citizen, there's a 12% chance that you're going to be living in poverty. Okay. So let's talk about independent events. I've never used the word independent yet, but I've actually talked a little bit about it. Okay, well, I just didn't do it in terms of saying these are independent events. So events are independent. Knowing event B occurred does not change the probability of A occurring. Go back to when I was talking about the coin flips. If I knew I had a head on the first toss, did that change the probability of getting a head on the second toss? And we answered no. And I actually showed you two ways. One way was based on the fact that you just knew that. The other way I showed you the sample space of doing the head, tail, tail, head, and tail, tail. Okay, so those two events are what we call our independent. I could care less about the first toss because it's not going to change what happens on the second toss. Okay? So if events are A and B are mathematically independent, then we know that the probability of A given B would just be the probability of A. Okay, back to the dice. I'm sorry, the coins. The probability of getting a head on the second toss, given I got a head on the first toss, is the same as getting the probability of getting a head on. a head on the second toss. Okay, because who cared that it was what we got on the first one? Okay, so. Okay, back to, remember how I rewrote all those formulas. That means that the probability of A and B is going to be the probability of A times the probability of B. Okay, because you remember this one of the ways I wrote the formula was the probability of A and B equals the probability of A given B times the probability of B, but we know the probability of A given B is just the probability of A. So that's where this here comes from. Okay, so let's look at something to determine if it is independent. Okay, so two fair six-sided dice are rolled. let S equal 7 be the event that the dice sum to 7, right? So we're going to add up the two numbers. And let D equal 4 be the event that the first dice lands on a 4. Are A and B independent?
Okay.
The first thing we need to do is we got to go back to thinking about what my sample space is. Okay? Okay, well, hang on. The first thing we need to talk about is what does it mean to be independent? Okay, think about what we just had on that other slide. So if the probability of A given B is equal to the probability of A, or if the probability of A and B equals the probability of A times the probability of B, then we know the events are independent. Okay, so if we think about the sample space now, okay, what is my sample space? This is back to that diagram I had earlier, okay, with all the dice throws. So there's actually 36 possible outcomes if you think in terms of what's on each dice. There's 11 different sums that you can get, okay, but there's 36 possible outcomes when you do it. Okay, so first we're going to need to write, using notation, write down the probabilities that we know. Okay, right, because we're looking to see if getting a sum of 7 is independent from having the first dice throw of 4. So we should be able to find the probability that the sum is 7. Okay, so look over in your table and you should be able to find all the cases where the probability, all the cases where the sum is 7. Those are why I circled in green. Okay, and we said there's 6 of those out of 36 possible dice throws, or 1/6. Okay. Now we should also be able to find the probability that the first dice was a 4. Okay, so just for this purpose of this here, we're going to consider the first dice throw being the dice across the top, and the second dice throw is going to be the one down the side. So you can think of two dice, one's kind of tealy color and the other one's yellow. My teal colored one is my first dice. Okay, so what's the probability that the first dice is a 4? You can either just say it's 1/6, or if you look at all 36 possibilities, you say, well, 6 of them had a dice throw of 4 out of the 36 total. So hope that 1/6 you get in two different ways. Once using all 36 outcomes, the other way just thinking what's the probability of getting a 4 when you roll a dice. Okay, so now I know the probability, in this case I know the probability of A and B, which is a sum of 7 and dice of 4. If you notice, I color coded some stuff up here so it can help you out. So I'm considering A my sum of 7 and B think of it as the dice throw of 4. Okay, so if I can find the probability that the sum is 7 given the first dice is a 4, and I can look to see if it's just equal to the probability of A. Okay, so if I look over here, I'm considering just these six couple outcomes. So my denominator is going to be a 6. Of those, how many had a sum of 7? Okay, and you said, oh, that one. So 1 out of 6. Okay, and you notice that's the exact same thing I got for just the probability the sum was 7. So that's up there. Okay. Next, the probability the sum is, so actually we now showed that they were independent, but I'll do it another way also. What's the probability of sum of 7 and the dice 1 equals a 4? Okay, that's again just this one case out of all 36. Okay, but if they're independent, now using this, is that the same as the probability of A times the probability of B? Right, so probability of the sum is 7 times the probability of the first dice is a 4. That's this 6 out of 36 times this 6 out of 36, which is 1 out of 36, they're the same. And you see, yes, the two events are independent. And we'll do a few more examples here in a little bit.